sense. It's kind of weird because like adding more points seems like it should make stuff slower, but we're kind of trying to avoid that. And so to make that work, we kind of like the points per bucket. Let's call that like X. We'd like that to be not really depend on the number of points, right? How do we compute the number of points per bucket? Assuming that things are kind of evenly distributed throughout. Yeah, so do the number of points divided by the number of buckets. Okay. Which means that if I want this to be kind of not depending on n, is there a way to make that work? I want this x to not depend on n. What can I do to make to kind of cancel out this n that I have up here? Yeah, so somehow this number of buckets has to depend on n as well, right? And that way, you know, as I increase n, I'm also increasing the number of buckets, so the number of points per bucket stays kind of the same. Does that make sense? Okay. So if the number of buckets is if we split in all the dimensions evenly, right? So this is number of divisions raised to the dimension. So we can have our number of splits be like the n to the 1 over the dimension power. So if we had 3-dimensional data, we'd have like, we took cube root of n divisions, then as I increase n, the size of my bucket stays kind of constant in terms of the number of points. Right? This is just one sort of option. You could, you could pick a constant and try different numbers. You could try other functions of n, but this is, one way you could come up with the number of divisions to kind of try to keep the bucket sizes independent of n. Does that help make any sense? So if I have one division in each dimension, I have one bucket, right? So the number of points in that bucket depends very heavily on n, right? As I add more points, in order to keep times reasonable, I kind of want to add more buckets so that the buckets don't get too big and so my local searches are fast. Because otherwise, I'm not really doing I'm not adding any value by doing the buckets because the buckets are way too big. So this is a way to kind of try to scale the number of buckets I have by the number of points to kind of keep things reasonably sized. And you might tune this. You might look at the average points per bucket, or the percentiles of points per bucket, right? And if your median bucket has 1 million points in it, probably you should have more points. You should have more buckets, right? And if your median has 1, then probably you should have fewer. Right? So you might want to actually look at how the points fit into the buckets to tune this, but this is kind of a starting point for where you might look. So yeah, this is I don't think there's a right answer to this. This is something that seems reasonable to me, but I encourage you to play around, try different ways of picking your number of buckets and see what you get. Yeah.
We talked about how to find the bucket in which to put a point.
Mm-hmm.
Right? We said p minus corner. Is corner like the min x and y value of all the points?
Yeah, so this would be the corner when we talked about it in the notes.
And then bucket size, I wasn't sure exactly what that meant. So
that would be the length of the bucket in the dimension you're looking at.
So how would you compute that when you be able to account for multiple dimensions, like 2 or 3 or 4 dimensions?
So each dimension is going to be different. So I would use the point class to do that independently for each dimension. So yeah, thinking about how you would do this, right? You have a bunch of points. First off, you kind of have to decide what region of space your buckets are going to cover, right? So I need to know what the dimensions of this are before I can start putting points in here. And so how could I figure that out to start with? Yeah, I want to find the min and max of all the points. So there's a function I gave you that does that. Gives you the AABB of all the points, and that gives you the range in all the dimensions. And then for each dimension, if you divide that, so you can get the length of each dimension by subtracting the min and the max, which will probably be different for each dimension. And then you can get the bucket size of each dimension by dividing by the number of splits. So I think it's easier if the number of splits is the same for each dimension, so you just have one int for the number of splits. But the size of each bucket is going to be a little bit different for each dimension, because the points are probably, the min and max will be slightly different. Other questions?
What's a good starting point? I rewatched the lecture on the buckets and stuff, and I read all the comments that were in the skeleton code and read through the points class and all that. It just seemed like I'd get to the spot where okay, I think I know what I'm doing, and then I just moved it.
So I would say there's a couple things you might do. One is you might start by building a dumb data structure to test with. So the dumb data structure would be, it would just loop through all the points. Okay. And you can do the queries with that, and that gives you something to test against as you're developing all the others. And so start by working with 10 points, right, for all these data structures, right, so that you can make sure you're getting the right answer, and you can run the dumb data structure, and it's small enough that it's instant, so you're not waiting around to verify that you're right or not. Yeah, and then from there I would start with probably the buckets. So the constructor, which is going to need a couple of the helper functions, and then probably the range query is the next easiest. In general, the range query is a little bit easier than the KNN. And then the tree ones are pretty different from the bucket. So if you get stuck on one, I would say work on the other. Definitely shoot me email, ask Alex questions as they come up. Yeah, I would start with the range queries on the various ones.
Can we go back to p minus the corner divided by bucket size? So you said, so you get the length of each dimension by subtracting your min and max values for each dimension. And then what is this?
So the bucket size, right, the length of this thing is the length of this divided by the number of cubes, right? So the bucket size is the max minus the min divided by the divisions. And then the corner is just the min. And so to get the bucket index, I just take my P minus the min and divide by the number of divisions. And then, you know, cast that to ints. So what we're doing there, right? If I'm less than one bucket size over, P minus the min is going to be. Oh, sorry, that's not. If I'm less than one bucket size over, when I do this and I cast in, I'm going to get 0. If I'm between 1 and 2 bucket sizes away, I'll get 1, and so on. So basically, this is like we're doing like a truncated division kind of thing here.
So max minus min, we have to do that for each division, for each dimension side.
Yep. So these are, I'm kind of writing these out as vectory type things, but you could wrap them in a for loop basically. I think I've overloaded some of the operators. So some of these might naturally work as I've written them. You can add other overloads if you want. Yeah.
And that was just over there, instead of passing in the divisions, just calculated based off of,
Yeah, so
based off the dimensions.
to test with, I would start by just passing in like 2, right? So start with like 1D or 2D points with like 2 splits, right? You can print it out, you can see, you can pick the points, right? And then so you know exactly like what you're working with, you draw a picture, you can see, and you know, make sure you're getting everything exactly like you expect, right? Scale it up a little bit, compare it against the dumb data structure, which should be like, you know, 2 for loops in there, right? And you can, you know, be more and more confident that you got it right as you go.
Yeah. Are you aware of any tools that could help to visualize something like this?
Yeah, if you dump out the points as CSV, then you can use pandas and just scatter plot. For the other stuff, like the bounding boxes, I don't know that there's an easy way to draw those. I think I gave you like overloads to print them easily. And so if you have a small enough amount of data, then that's probably the easiest thing to do, is just do some printf debugging and see. So eventually, yeah, you're going to time basically running these data sets, and then do some analysis on the timing. Yeah.
Is that pretty involved? Is that
so you're going to have, so that's going to be least squares regression, basically. So that is going to be pretty similar to like what you did for the Hacker News or real estate. So, and there's only, we're really only looking at regression on one variable. We're looking at basically time as a function of the number of points. And we're going to do that for a bunch of different techniques and just compare them. So yeah, the regression part's not that, this is probably much less time intensive than the implementation. Is anybody taking a look at the tree ones? I would say if you have time today, look at the bucket, see where you get, and then take a look at one of the tree ones. some things are a little bit easier with the KD tree, some things are a little bit easier with the quad tree. So they're both pretty similar. So I don't know that it really matters which one you pick. Again, take a look at that, bring questions for tomorrow. We can talk more about that. Any other questions?
Yeah, just one more with the bucket. In class, it looked like we had it as a 2D array data structure, and I was curious if there was any trade-off with doing an unordered map.
What are the keys and values
I guess you would just do an X and Y.
for the key?
Or, sorry, like X for.
So my map, right? I'm going to have a map
Mhm.
from key. So I have some key, some value.
Yeah,
So
and I
what
guess I
is
was
the,
just thinking points, so like you do your X, Y.
so the key would be the point,
Mhm.
and the V would be what?
Oh, sorry. No, I was thinking like the actual X, Y, it would just be an unordered map of your points per bucket.
So this
if
would
that
be
makes sense.
like X, Y.
Mhm.
So what happens if you have 2 points that have the same X coordinate?
Not a big point. You just don't get it, I guess.
So that you could use a multi-map. So again, the hash table is actually, this is one situation where the hash table is really bad because for the hash table, you have to know exactly what you're looking for. Whereas here, we want a range of things. So the hash table for point location is actually, this is one of the applications where it's just not very good at. So the kind of the tree-based or spatial partition data structures work well here because we need a range of stuff. The hash table won't help us out. Any other questions? Yeah.
So if you have max, minus, and min, to me that would give a point of dimensions with coordinates, right? A difference between the max and min for each coordinates.
That's the length of
Yeah.
the area we're looking at in each dimension.
And then how do you divide that by a number, like division? Is that
So-
dividing each coordinate by that number?
Yeah. So I don't know if I think I overloaded the division operator in the point class, maybe. So if I did, then it would be, if you divide by one number, then it just does component-wise, and if you divide by a vector, it's each component. Yeah. If I didn't do that, you just do it to each component. Any other questions? I'm certainly aware that this is a big assignment, so I'm happy to take lots of questions. Yeah, work on it, bring more questions tomorrow. Cool. All right, so the plan for today is we're going to do analysis of another data set, just kind of look at the three most recent classification techniques we've looked at, and we're going to have a little competition. Before that, we're going to talk about a related concept or kind of a useful tool that can help us before we jump into building our models, called feature selection. Okay. So if you all remember, when we looked at the Titanic data set, there was a whole bunch of features of the data, a whole bunch of input variables. So we had age, sex, class, the location they started from, the number of spouses and siblings, all that sort of stuff, right? And when we built our model, we didn't use all of them, right? Feature selection is the process of trying to, before we build a model, understand which features are likely to be good predictors of the output. So we did sort of a after the fact feature selection when we did least squares. So we had all this real estate data, and the models you came up with were usually based on like two things, or two or three features. How do we go about doing feature selection there?
After doing the regression, you have a p-value for each individual component. P-value in this.
So there was a p-value as part of it, and there was another. Yeah. Right. So when we did regression, we could fit a model, and then we could look at the R squared and the p-values. Right? And these told us, the R squared told us if we had two models, the R squared told us, kind of, we could compare the accuracy of the models of the data, or the fit of the models to the data, right? And then the p-values told us, okay, well, if I'm going to simplify my model, which of these features is least likely to be useful, or, which one is least likely to cause problems if I remove it. Okay. So this was kind of it was practical for us because the least squares models are really fast to fit, right? So we could make a model, and then 2 seconds later we could look at the R square value, try a different model, right? So we could iterate on this, and it was fast. The least squares models give us this information to work with, right? So we have there's R squared and p-values, are computed as we fit our model. So we have access to this information to understand it. What about something like KNN or SVMs? There's not really a corresponding R squared type thing for either of those. Right? We can look at our accuracy on like a testing data set. We can look at our confusion matrix, that kind of stuff. But we don't get anything like a p-value out, right? And so for those types of models, what we'd have to do is we basically have to remove columns of our data, fit a model, see how good it does, do that a bunch of times with all the different combinations of features, right? And try to figure out which one works best. And for the decision trees, right? Our construction algorithm tries to pick the best one, but it might be nice to kind of prune ahead of time which features we think are going to be useful and which aren't. Okay. So today we're going to talk about one technique for doing feature selection before we build our model. And so we can, before we spend the time to fit a model, which could be expensive, right? So fitting an SVM on a big set of data might be really expensive. So we can do some feature selection ahead of time to pick which columns of our data we think are going to be important. Okay. So the one technique we'll look at today is called the chi-squared test. And basically, the idea here is chi-squared test is a hypothesis test. And our hypothesis is that basically that two columns are independent. Okay, so that's our null hypothesis says, hey, these columns, there's no relationship between them, right? So I could more or less analyze them independently. If my columns are independent, if one is my output, right, and another column is a feature, if they're independent, should I use that feature as part of my model? No, right? They're independent, so that feature I would expect does not tell me much about the output that I'm interested in. Okay. So the chi-square test tries to see, like, it's a pretty simple test to see, like, are these things independent or not? Okay, so we'll look at a simple example, or simple, simple example, kind of like we saw in the Titanic, just to give you a sense for how it works. We're not going to dive into the math too deeply. But so let's say this is our Titanic data set. And so we have for the men and women, we just are going to do some crosstabs on who lived and who died based on sex. Okay. So let's say the men, we had 10 live and 90 died. Women, we had, let's say, 30, 20. Okay. So what we're interested in is we're trying to figure out, is the sex a good predictor for whether or not you've lived or died on the Titanic? And from our decision tree, after we fit models, we saw that, yes, it turns out that it is. But if we just look at this, it's maybe not immediately obvious, right? Just at a glance, it seems like the men were more likely to die than the women. But there's a lot fewer women, so, is it statistically significant? We're not sure. So the chi-square test lets us compute, it gives us the actual probability that these things are independent. Okay. So the basic idea is we just look at the total fraction of people that lived or died, and then we compare the fraction of the men and the fraction of the women to that to see how far off they are, right? And if they're way different, then we can conclude that they are not independent, which tells us that we should include this feature in our model. Okay. So for the men, right? So for the men, the actual survival rate is, what, 10%? For the women, the actual survival rate is 60%. And the total survival rate was not a number that I can usually compute. Anybody want to calculate that for me quick? Cool. All right. So now we have a little bit better of an idea, right? It seems like this is pretty far off from the total population. This is pretty far off from the total population. So probably there is the sex is not independent from whether or not people lived or died. So what we compute basically is for each of the possibilities here, we compute basically how far off it is from the average. So we compute. I'll just write out the formula just to show it. So the observed is the survival percentage for men. The expected is the survival percentage for everybody. Okay. And so we compute this for men, compute this for women, add that up, and that is our test statistic. test statistic. This is like the z-score we got or whatever. Okay. So that gives us our test statistic value. Okay. The test statistic is assumed to come from, it's called the chi-square distribution. And it looks something, so there's some parameters, but it looks, as the parameters get bigger, the lines kind of get further over, but basically large values are less likely than small values. Okay. So the larger a value here, right, the further each of our little subsets is from the total average, right, the higher our test statistic is going to be, which means the less likely that these things are independent. And so we compute a p-value based on the statistic we compute and the chi-squared probability distribution, right? And if the p-value is very small, then that means that there is a relationship between these two features, right? And so we should, include it in our model. Okay? So in this case, for our little Titanic example, right, our test statistic is going to be pretty big because both the men and the women are very far away from the total average, right, survival rate. So they're going to have a large chi-squared statistic value, which means they're going to have a low probability according to the distribution over there. And so we can conclude that sex probably will be a very good feature to include in our model, and it has a big impact on whether or not people survive. Okay. So that kind of makes sense. So it's a hypothesis test. To use it, basically what you have to know is you get out p-values, and then the p-values tell you the probability that the feature is independent of the thing you're interested in. Okay? If the p-value is low, then you probably want to include it in your model. Any questions about that? All right, cool. So let's go ahead, we'll take a look at the data set. Oh, I think I forgot. I forgot to upload the data set earlier, but it should be up there now. So what we have here is some like public health kind of data that we're going to look at. So we have some information about women in, I believe, Indonesia, and we're interested in basically understanding contraceptive use among the population. Okay. So we have some survey data from, looks like about 1,500 women. And so we're trying to figure out, can we predict anything about contraceptive use based on data that is a little bit more easy to acquire, right? So to get information about contraceptive use, right, you have to do interviews, you have to ask people, right? For other things like age or the number of children, stuff like that, right, you could get that from the census, right? So maybe we can predict this other data. We can predict something based on data that's easier for us to come by, right? And if you're working in public health, this might be really important for you to be able to do. So that's kind of that's the scenario, right? So so we know. So we have some information about the women from the survey. We know their age, their education, their husband's education, number of children they've had, whether they're Muslim, whether they're employed. This is a weird. don't know why those seem to be backwards, but might do a little bit more data cleanup if we were going to pursue this longer. You have the type of occupation of the husband, standard of living, and then this is the label that we're trying to predict. Basically, what contraception methods are they using? So, if you're, a NGO or something, and you're trying to you're trying to increase contraceptive use, right? You'd want to figure out which of these features has the strongest impact, right? So you would know, where to put your efforts for, some sort of campaign. So that's kind of the setup, right? So we'll look at some parts of this together, and then we'll have you work in teams to try to come up with predictive models, and we'll see who can come up with the best model. So all our import stuff. So this is our data set. Just if we look at a little bit of it, so we have age, education, all this stuff. And again, this is the column that we're trying to predict over here. So if we describe the data set, so it looks like the mean age is early 30s. The mean education is relatively high. The mean education is 3 out of 4. And it looks like at least a quarter of the population has the highest level of education here. Looks like the husbands tend to be slightly more educated in this data set. An average of 3 kids. Looks like 85% Muslim. High employment. Is this a useful value?
I mean, they mix it.
Yeah. Right. So the contraceptive method was categorical, right? We're taking the mean, right? So that there's kind of an ordering here. I think 1 is none, and 2 and 3 are some sort of contraception. So you could maybe argue that there's some sort of meaning, but here it's kind of weird to take the average of a categorical value. So this is the label we're trying to predict, and these are basically what the values of that, what the numbers correspond to. These are all the other features in our data, and then these are just a subset of the labels. Okay. So maybe the first thing we might want to look at is, like, is there actually a distribution of the different contraceptive methods, period, right? So, like, if everybody's using one method, then maybe we don't even have to look at the other features, right? We just, we can predict based on nothing, just based on just the population. Say, hey, like, probably that's the method that people are using. So we'll start by just looking at the contraceptive method for the whole population, and then we can see that, okay, well, there's certainly some variation here. They're all 3 groups are pretty well represented. So looks like we probably want to dig a little bit deeper. So maybe the next thing we might look at is, maybe it depends on age, right? So we can look at just a histogram of the age. So it looks like we have a bunch of kind of teenage to middle-aged women in our data sets. And so Next thing is to maybe pull out and look at what the contraceptive use looks like based on age. So we'll look at a factor plot, right? So we're going to look at 3 histograms. So the age is going to be the bin thing, and then we'll have 1 histogram for each contraceptive method. So we look at that. Does anybody gain any insights from here? Is that 2 or 3? 2? Okay. So yeah, long term seems to be most popular, kind of regardless of age. It doesn't seem to have a, so I guess maybe the other things is that short term is less popular amongst the older women. All right, but other than that, I don't see a whole lot of other trends here. So it looks like, again, we might need a more sophisticated model to kind of try to understand what's going on here. So we'll maybe look at seeing if employment has a big impact. Conclusions from here? It looks like the relative use rate is about the same when independent of employment, right? So for whether or not they're employed, method 1 is the most common, method 3 is the next most, method 2 after that. So the employment doesn't seem to make a big impact. So I think we're going to need a more sophisticated model to understand this. So we'll look at how we might develop one of those more sophisticated models, and then I will leave, and then in pairs we'll actually give it a shot and see what we come up with. A couple of helper functions. So it's the train test split function. So we provide the features we're interested in, and then we can get the training testing data. And then we'll take a look at the feature selection tools in scikit-learn, just to kind of see what they look like in practice. We will use the chi-squared test to get the p-values for the various features to see which ones are likely to be useful in our model. Let's see what we have here. So these are all of our features, and here's the corresponding p-values. So of these, it looks like age is actually has the smallest p-value. So it is, the least independent, right? So it looks like we should definitely take age into account as part of our model. Which other features seem to be most likely to be useful in our model? Looks like education is next most. Number of children, and media exposure. So if I am working for some sort of NGO, this probably makes me pretty happy that I can advertise my way into achieving whatever goals I have. Okay. This is just going to show us the p-values for all the features. This select k-best method just uses the chi-square test and gives me the features that are the top k. I'll look at the features. The get support just says true or false, is it one of the top k? And then these are the ones I selected. So as we saw, right, the age, education, and number of children were the most predictive. So these were the ones that were selected. If I went up to k equals 4, it looks like we get media exposure as part of that as well. We'll add that one in. Right. So this has kind of narrowed it down to what features might be useful for a model. Okay. This is some helper code to draw a decision tree. So if you use the decision tree model, then this will be helpful for kind of understanding that. Okay. All right. And so at this point, we're going to do kind of a lab. So I'm going to leave the rest of the analysis up to you. We'll kind of go through it together at the end. So the first thing is, basically, we looked at age and education, and to get a sense for how they impact the contraceptive method. So let's do similar things for the other labels that we thought were important. And so number of children, maybe media exposure. So we'll get an understanding of how those are important. And then we're going to build models to do prediction and see how well we can do. So we will be looking at decision trees, KNN, and SVMs. And so your job is to work with a partner, fit these models, and see what kind of accuracy you can get on this prediction challenge. And then we'll compare and talk about what people are able to come up with together. So grab a partner, either just download this notebook or clone the repo. And there's a data set that is also in the same folder. It's this cmc.csv data set. And start working through these tasks at the bottom, and then we'll come together to see what people are able to come up with.
I'm going to do that.
It seems to be working so far.
I know the answer now. Yeah, no, no water. This one right here. I don't think okay. I guess it's all the other variables.
There's one of the pictures. That was my understanding. So I just copied it. You already looked at age and education. When did you do education?
So, education.
Even better.
I'm just seeing where it's getting. So.
Just did the basic.
Right here.
Is that on GitHub? Yeah, I think GitHub is.
Sometimes it works.
Yeah. 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 Microsoft product.
So they have different types. Yeah, it's just the head of that. Children would probably
Try to more than, yeah.
I mean, maybe that would be.
Oh.
Splits these up. You can see them 1, 2, 3 rather than the mixed in version.
That's it.
Yes.
Okay. So it actually is.
There's not much difference in educations for method
Or sorry,
1,
most.
or method 2, and method 3 is more education.
Or,
Seems to. There shouldn't be one in between. It's just, you know, it's just, education categorical low. So that no one should be classified as 2.5. It's just which means that doesn't fully make sense. For me, yeah. Because it goes in a range, you know, it makes sense in that sense, but otherwise. I did the children. I did education too, because it was in our list, so this is children. I did this one. This one has them all combined, so you can see them next to each other. I just used that one and just changed it to the.
Do we want any further?
I think that you can just change the variable from a void to
Education. I mean, this is my age, it's hard to.
The colors. So what colors are you? Yeah, I'm seeing that. I'm pretty sure, yeah. If we lose two, then
Did you have any questions on the homework?
Homework 3 was a little weird. Well, the description was, well, no one really
method is the cost percentage. So method one, method two, method three. So which cost percentage would you? So we'd still want it to be those because, so then, I know that's where I like it split up this way because
literally
this is
one
one child, but those are the three different methods.
It's just
We have one child. These
So
are
I think
three
the
different
current one,
methods.
the current,
The parents who have two children. So it's looking at the cost percentage. Yeah.
So do you get through the implementation of the data structures?
yeah, I didn't
I didn't keep
So
that
I
one.
don't see a correlation
But I
in
did
age.
do, I did want to
Putting down the
do each
implementation.
contraceptive method, so you could see those separately.
Different methods is kind of like our lines.
Oh, yeah.
It, yeah, it just puts it into the, how many people
So-
use that many. Yeah. And those people just copied the one.
Oh,
here.
expected use, okay.
So I just copied that one and changed the age to children each time, yeah. Yeah.
Contraceptive.
Yeah. It's really interesting in general. So I guess I'm interested, most likely there's not a whole lot of people who have children. So like, when we look at this, they all look about the same. So I'm not sure that tells us much else.
This one is different because the kind is. If we have
Yeah.
one child, so two or three children, then
It's section for,
so now there's two routes and.
So has anybody started using models and predicting yet?
counting decision trees.
Yeah. What kind of accuracy are you getting?
On test data, 55%.
Something in like the 50% range, right? So that's like a coin flip, right? Is that good for this data set? Kind of a trick question. The 50% accuracy here is actually going to be substantially better than a coin flip.
Eating like there's a bunch of variables.
The coin is maybe not the device. So a 33% accuracy would be pretty bad here. Why 50% is pretty good? How come? or it's you know, it's better than guessing. So how many classes do we have to choose between? We have to choose between 3 classes, right? 50-50, 50% accuracy, we're doing better than guessing, right? Because guessing we would expect to be like, we get it right a third of the time. So actually, you know, it's not not super high accuracy, but it's actually a pretty substantial improvement over guessing. So, yeah, if it was, you know, a yes or no question and we're getting 50%, then we'd want to worry. You probably want to look at like the total distribution, right? If we're just right, if we had kind of even numbers of yes and no and we're getting 50-50, then yeah, our models are pretty bad. But here, over 50%, we're doing something right.
Which is the same thing, just visually separated, so you can see it.
Although most of them, it's not there like that. 2, 0 is weird ones to me.
That just combined it. You know, like you don't want it.
Render tree. Generally, the first place I go for code examples is the note from. I would clone the repo and open that through your own oh, why? Either they changed the format recently or GitHub is something weird.
So processing.
See what happens first. That's. Yeah,
So, I just found that too. I was doing the same thing you were doing. Apparently we've already done that, so we can just skip to that. I think. Need to adjust these.
That's the one, what's your?
We were pulling actual columns.
the stats first.
Did that merge especially?
It's zero changes. I don't remember anything really at all, but you can merge out here with like the idea.
And then all I did was edit.
It's either no zoom or 150%.
Oh.
How many people have fit a decision tree? I may have tried one of the other methods. We'll take we'll do another 5 minutes or so, and then we'll come together and kind of see who is the ultimate classifier.
That's probably where my hair, I'm like, someone's going wrong. That was way better. You know, the picture. Thing that looks like a tree. I just put age in there. Because we wanted to look at age. We just already had graphed it. Because our 3 best were age, children, education. Yeah. Oh, best features. Look at that.
Oh.
Oh, how many? Oh, yeah. Yeah. So I usually go to search for any imports. Do you have this
For the KNN and the SPM, it will probably be difficult to visualize because we have like 3 categorical values that are our inputs. So visualizing that's not gonna do too much.
How about I found this point.
The previous code just run it, and it's like 8 an hour. So
That's true, that should be fine, it should be after that.
yeah, so I run it all the way up to this.
And that one worked, right, the one right after visualization, you installed.
Yeah.
These are the only ones I added in the decision. We did hide out, that's already.
Yep.
Oh, yeah.
Yeah.
Oh, yeah.
So let's take a look at the classifiers I came up with. So just to start with, to like compare, look at all the various methods. I started with just a pair plot to see, you know, if anything jumped out at me. These ones down the middle, the diagonal, are kind of a little bit interesting. They show you how the distribution is different for the different methods. So like on this one, we can see that the blue one, which is the education, right? The shape seems to be pretty different there. Right? So it seems like that might be an important feature to look at. The husband's occupation, maybe. So that's the one with the three humps there. The standard of living, it looks like all three shapes are like pretty similar. They're just kind of stacked on top of each other, scaled by the number of women in each group. So yeah, this didn't really help me out all that much, but you know, for some data sets, maybe it'll be useful. To look at the effect of education, we use the factor plot again. So we look at this. Anything jump out at you? Any insights from this? So it seems that more education leads to higher rates of contraceptive use. Right? So for the groups where they're using contraception, more education leads to higher use. So definitely that's probably something we should include in our model. Right? We look at the number of children. Looks like none of the people using contraceptives have no children, or maybe one person. Or maybe a little bit surprising, but maybe everybody wants kids. So maybe this is like family planning after you have children. It looks like the max number of children is 16, which seems like pretty crazy to me. Again, the distributions are different. Look a little bit different for the three methods, so that probably is going to be an important feature in our model. If you look at religion, does it tell us anything?
Non-Islam.
Yeah, so it looks like there are more Muslims than non-Muslims in this group. And it looks like the religious people tend to not use contraception more often than the non-religious people. That was like the worst way I could have put that. Religious people seem less likely to use contraceptive right here. For the non-religious, it's about a third. There's about even numbers in all the three groups. For here is much larger group of women not using contraception out of the religious group. So again, religion probably important for a mom. So take a look at our the classifiers. We'll look at a decision tree first. So we'll split our data into training and testing so we can do cross-validation. And we'll start by looking at just all of the features. And so here I have a depth of 4, a split size of 20 to try to deal with the overfitting, fit my tree, and then look at my training and testing accuracy, and draw out my tree. And so I was able to get about 56% accuracy on the testing data, almost exactly the same on the training data. So it looks like I'm not overfitting too much here, so that's good. It looks like this is kind of surprising to me what the tree looked like, but for the women that don't have children, this node doesn't seem very important, right? And if I were, going to use this as like a decision tree for my organization, I'd probably get rid of this node, right? Because there's only 3 people here. So this doesn't seem to be a very useful split. So it looks like the women without children tend not to use contraceptives. So that is an insight gained from the decision tree. Beyond that, looks like age is the next most important factor. And beyond that, it gets a little bit trickier to kind of understand to make sense of this decision tree in terms of explaining what's going on. Does anybody have better accuracy with decision trees? So try different parameters. So fewer. I'm also using all of the features here, so maybe if I just look at the best features and ignore the other ones. So it looks like my accuracy is about the same. I only considered 4 features instead, so this is just age, education, number of children, and I think that's it. And media exposure. It looks like media exposure was not important. Again, so this is kind of interesting. I got a different kind of useless split here than I did before. But still, probably didn't need to split this node. And the age, so the age was still the number 2, and then looked at education after that. So it's like we learned something from the decision tree. This branch over here kind of gave us a new insight. Unclear what the causation is, but something useful to know. And we got reasonably good accuracy. So almost twice as good as guessing. All right. KNN. So we're just going to use the K nearest neighbors classifier. I picked K of 30, and then we'll just look at the accuracy of the training and testing data. And this looks, I did slightly worse, which was a little bit surprising to me. I'm only looking at the best features, so this was before. And I have a K of 30, which is maybe too big. Did anybody play around with K and find a good value? maybe I'm overfitting a little bit. My training accuracy is a bit higher. Okay, I have 15. Somehow that made it worse. That's very surprising to me. Maybe I should look at all the features instead of just the best one. So if I look at all the features, it looks like my accuracy scores went up a little bit. But there's still a pretty big gap between my training and testing data. So about 30 neighbors does seem to be a reasonable choice, I guess. Yeah, my accuracy is a little bit lower than it was for the decision tree, which is a bit surprising to me. And then the last one, we'll look at the SVM. So I'm going to use the RBF kernel. This gamma, so remember that's like it's a power that shows up. So it's another knob I could tune. And then C is my my budget. So again, a smaller C, it's going to be more sensitive. A larger C, I'm going to be kind of less sensitive to the points right by the boundary. So if we look at this, my test accuracy is higher than my training accuracy, which is, again, kind of weird. So maybe let me bump down my C a little bit, see if that changes. It seems to be getting worse. Yeah. It doesn't seem to be all that sensitive, my C value. My test accuracy seems to be kind of stuck at about 56% for all of these methods. Change my gamma a little bit. Looks like increasing gamma gave me a little bit of a boost. Yeah, so we looked at three different models for this data set. They all seem to work kind of about as well. The decision tree is the benefit of giving us kind of an explanation for where the for how the model works. So we got a little bit of insight from that. Yeah, they're all three seem to be about comparably accurate for classification. Any questions about this exercise? All right, so if you're an NGO, right, you probably want to pay somebody a lot of money to give you a model like this, so you can try to understand the population a little bit better. Right? You interviewed 1,500 people, and maybe now you can give predictions about the millions of people that live in Indonesia based on this other information, which is easier to collect. All right, cool. All right, so that's kind of a wrap up of classification. Starting tomorrow, we're going to start looking at what are called unsupervised learning methods. And these are methods where for our input data that we're training on, we don't really have a right answer as we do here. Right? So for this data set, we had for our inputs, we knew the label for all of our data points. Right? For starting tomorrow, we're going to think about what happens when there's not really a right label. We're trying to understand our data. We're trying to understand something about our data that's something we didn't explicitly collect. So that's what we'll start looking at tomorrow. I'm going to hang out for like 30 minutes to kind of do office hours for the next assignment. So if you can stay, I encourage you to start on that and ask me questions while I'm here, and hopefully can get you a boost on the next one.